Hey, welcome to today's colloquium. The speaker is Professor Shane Byrne, who needs no introduction to most of you, but in case we have some visitors, Shane got his master's in physics at the University of Wales, PhD from Caltech. He came to U of A in 2007 as an assistant professor. He's now effectively the PI of HiRISE, although we're still waiting on signatures for that. He's the director of the Space Imagery Center. He's PhD advisor for 3 current grad students and 8 former students and a couple of postdocs. And his research concerns Mars, ice on any planet or body, and landscape evolution.
All right. Hopefully everybody can hear me all right. So wave your hands if I'm not coming through. Okay, well, it's great to give this talk, and it's a fun subject, so I hope this will be entertaining for everybody. I'm going to talk a bit about these super steep scarps that are around the edge of the North Polar Cap on Mars, and some of the dramatic activity that we see there, including avalanches like this, which are extremely common, it turns out. Before I start talking about the avalanches and these cliffs and stuff, I'm going to back up a little bit and talk about where they are and why it matters. And we study ice around the solar system on Earth and Mars, especially as a way to record environmental conditions that are going on. And this might even be true of like ice in lunar permanently shaded craters as well, where there's just a record of delivery of comets into the inner solar system over geologic time as well. But on the terrestrial planets like Earth and Mars, these ice deposits and the layers in them are recording climate fluctuations. There's 4 big ice sheets in the inner solar system that we like to study to do this. One of which is Antarctica, which is not on here, and it's bigger than all these 3 put together. But the other 3 are pretty comparable in size. There's the North Pole of Mars here, the South Pole, both about 1 million cubic kilometers. And then there's Greenland, which is a little bit more, maybe about 5 or 6 million cubic kilometers or so. But they're all more or less comparable in size and thickness, and they're all heavily layered with information that relates back to the climate of these bodies. Down the bottom here, and I should have obeyed my advice that I give to all my own students, and don't put important figures down the very bottom of your slide. But down at the bottom here, you see some of these layering that run through the North Polar layer deposits on Mars. This is about 1,000 kilometers from end to end here from this picture, and about 2 kilometers worth of ice in thickness. Most of the time, we're studying these layers in cliffs where they're outcropping, where we can look with HiRISE imagery and stereo DTMs to figure out what's going on. And after lots of years of studying this, there's a large community that's built up, and the general consensus is that there's about 4 or 5 million years of history represented in about 2 kilometers worth of ice there. And that sort of history is reflecting the dust ice composition of the ice, of the material here. And going back over time, a lot of effort has gone into trying to link these to orbital variations, such as like how obliquity on Mars varies over time. So there's 10 million years of obliquity variations here. And just for scale, I put in Earth's obliquity variations in green here to give you an idea of how much the climate on Mars changes compared to on the Earth. There's orbital eccentricity variations on Mars as well, and they all feed into variations in the amount of sunlight that's hitting Mars's North Pole over time, which can vary by like a factor of 3 or so, even over this short amount of time here. So lots of variations in the meteorology of Mars and movements of ice from areas that are stable today to unstable, that have come from places that are now unstable, and vice versa as the climate shifts. Okay, so a lot of these cliffs that we use to study the climate record then look much like this. And these are the troughs that you can see here, the dark lanes in the North Polar Cap. So this is about the dome of 2 kilometers thick of ice. These troughs are only a couple of 100 meters in relief, but they're very shallow. So this is a 40 times vertically exaggerated topographic profile over this particular scarp. Let me get rid of my mouse pointer here. And so these are only a few degrees in slope, but when you look at high-rise images, you can still see the individual layers here, and you can zoom up even further, and you see that they're covered in this dust deposit, which is probably a sublimation lag from the ice, and it's at least thick enough that it's slumping down slope in places, but it's probably not all that thick, probably only centimeters or so, because these scarps or these troughs need to continuously retreat, as we can see in the radar data of the geologic record here. These scarps migrate poleward due to ablation over time. So the dust layer can't be all that thick, but it is present. That's in contrast to the scarps we're going to be talking about today. So these are very steep cliffs that ring the edge of the North Polar deposits. So again, on a map view here, all these red areas are the very steep slopes, above 35 degrees in this representation, but really most of the cliffs we'll be talking about today are closer to vertical, and many sections above 80 degrees, with 70 degrees even being common. It has this, when you zoom up, this jagged appearance of these slabs of material, or these flaking, or these flakes of material that appear to be separating from the cliff face itself. And it's so steep in places that it's possible that there's even some overhangs here. There's lots of debris at the base, so clearly these cliffs are back wasting at an impressive rate. And we do have some stereo DTMs, although they're extremely hard to make because you try to take images from different angles of these cliffs, and they're 80 degrees in slope, so you can only look from one direction because you can't really look at it from the other direction, because suddenly the cliff face is occluded and you can't even see it. So the stereo DTMs are tricky to make, and some of my co-authors like Sarah Sutton and Chris Akers have been working hard on trying to actually get a stereo solution to converge on these cliffs, and the results are really nice when that works out. So this is just one of those cliffs here. There's no vertical exaggeration in this DTM or this perspective view here. So this looks like a vertical step in this image because it really is. There's about 800 meters of relief in this case. So that's that would look extremely impressive if you were standing at the bottom here. An 800-meter high vertical wall is something that we don't have much experience with on the Earth. But then, just for the Game of Thrones people out there, planetary analogs take a lot of different forms. And if you have watched the TV series or read the book, then you probably know about the Great Ice Wall here. And the Great Ice Wall, as far as I remember from the books, is only about 800 feet tall. So it's about, the Mars cliffs are about 3 times higher than this, but equally steep and impressive looking. And you probably won't find this guy on Mars, but there's all sorts of other interesting things to see as well. Okay, so they're extremely steep and impressive looking, it's true, but there's also a lot of activity going on these cliffs. So if you look here at images that are differenced by 1 year, so there's another high-rise image of this particular cliff face. We'll keep coming back to this one because it's been studied so intensively, and we have so many images of it. But the others are just as interesting, I should say. And a machine learning approach looked at where there were differences on the cliff face from 1 year to the next. All these little red dots here on the zoom up show where blocks have fallen out of the cliff face. All the blue dots down below show where there are new debris. So there's hundreds of locations where there's stuff falling out of this cliff face, and hundreds of locations where there's new debris appearing at the base. So that's pretty indicative of like a very active area. There's even some very large ones as well. Like here's 2 high-rise images separated by a year-ish, more or less a year. And there's a 70-meter wide section here, a giant slab of ice that's just kind of sloughed off, and all this new debris here is mostly off picture. There's a big debris field of boulders right there. So just for orientation, the high area is down here, and we're going down to the very base of the cliff here. So right at the base, this area has kind of broken off. But the activity doesn't end with that. So there's also extremely active avalanches in this area, but interestingly, just at one particular time of year. And you know, it was incredible when we saw these first at high rise, like there's an active avalanche in progress. You can imagine looking at it from an airplane window as you fly across, I don't know, any mountain range on the Earth, and ask yourself what the chances are that you would see an active avalanche in progress. probably minute, right? But we saw one of these in high rise and thought that was incredible. But then we started seeing them all the time. They're basically extremely common on these scarps. So a bit of a rogues gallery is here of some of these features. You have like these large clouds that are clearly like running down the cliff face and billowing out of the bottom. There's even like small detached clouds from an avalanche that occurred just previously over here. Some of these are caught just right after their initiation, and they haven't even run down the cliff face yet to move out at the bottom. So we're seeing all phases of the lifespan of one of these avalanche events in the high-rise image, dozens of them, in fact. And even one image has 4 simultaneous avalanches going off at different parts along this cliff. So this image spans, I don't know, maybe 10 to 20 kilometers of cliff length here, and dotted along this, you see in 4 different locations, an avalanche, or 4 different avalanches in progress. Okay, so one of the really cool and interesting things about these avalanches is that they're very confined to a certain season, and this is going to be key to kind of understanding what's going on here and what's causing them. So this is a histogram of number of images taken in the pink here over much of the Mars year. So Elsebes is our measure of season on Mars, and Elsebes 0 is the beginning of spring here in the Northern Hemisphere. So there's some images taken in late winter, and we'll talk more about those too. A lot of images taken in the spring from Elsebes 0 to 90, and then a lot of images taken in the summer, Elsebes 90 to 180. And you can see that we've got pretty good coverage. This is number of images on the right over all of these daylit seasons. The avalanches that we see occur in the orange images here. So there are some times of year, like this Elsebes 35 to 40 bracket, where every single image we took in that Elsebes range of these steep scarps had an avalanche in it. And it's not a small amount of images, right? There's like 20 images in that Elsebes bin of these steep scarps. So these are extremely active, but in a very narrowly defined time of year. There's a kind of like a long ramp up period here where maybe 20% of the images contain an avalanche, or a little bit less, up to a point where every single image has an avalanche, and then a steep drop off where we don't see avalanches past this Elsebes 50 mark. The other interesting thing is that this avalanche activity varies a lot from year to year. So down on the bottom here, we have Mars years along the bottom now. And this time, instead of looking at all scarps, we're just looking at that special scarp that we've been showing all the pictures of, because we've got lots of data there. So we've got Mars year 29, the first Martian North Polar summer that we started on, and springtime rather, and then up to Mars year 37. We did just acquire Mars year 38 worth of data, but we haven't looked through the images yet. This is the number of avalanches per image. You can see that it exceeds 1 some years. So this is just for the Elsebes range where things are, where things are active in the springtime here. So because there's multiple avalanches per image, sometimes the number of avalanches per image is greater than 1. There's an interesting trend here where the number of avalanches per image seems to be going down, and not just over 1 year, but systematically over several Mars years. And this is very puzzling because the Martian climate is supposed to be basically the equivalent of a goldfish, right? It doesn't have any memory of where it's been or where it's going. And it's more or less just a metronome that keeps rocking back and forth. And even in years when there's global dust storms, which are major events on Mars, you look at the atmospheric temperatures and circulations a year later, there's almost no memory of the dust storm event that has happened. So to see a trend like that has a multi-year consistent direction is very puzzling, and might indicate that there's something more to the Martian climate than meets the eye. Or maybe it's tied to the cliff faces themselves. As we'll try and talk about what's causing these avalanches, we'll try and tease those things apart later on. One of the other neat things that we can do with HiRISE is take movies, very short movies, very, very short. But for things that move very fast, that's okay. And these avalanches, it turns out, move quite fast. So HiRISE is a push broom camera with the different colors at slightly different places on the focal plane. So red images, blue images, infrared images, they're all basically at slightly different times. And you can put those together into an animated GIF, which is static 99.99% of the time, but for occasionally dynamic phenomena like dust devils or avalanches, you can see some movement. You can also measure the movement and see how quickly these things are moving. And these avalanches are moving at several meters per second when we image them. So we're seeing lots and lots of avalanches, but it's not because an avalanche is a very slow process that takes hours and hours to run all the way out. They're running out in a minute or two. And yet still we're seeing avalanches in every image we take in some times of the year. So they must be incredibly frequent. And you can imagine some future tourist attraction, right, where there's a viewing platform, National Park Service attendee, just showing people in. You can just sit there for a couple of hours watching avalanche after avalanche come down these cliffs. But they are exceptionally frequent, and we will get a formal estimate of that frequency later on. But just intuitively, you can tell by the speed they're moving at and the number that we see that they must be very, very frequent. Okay, so the challenge then is to try and explain what's going on these scarps. So we've got this weird slab-like texture here. This is a blow up of the yellow box on the right, showing all these slabs of material which are clearly falling off because before and after images show changes on the scarps, and there's new debris at the bottom. And we can even see some of the larger sections that are up to 70 meters come off all in one go. We also have these pervasive or this very frequent avalanches that in a certain time of year, with a very specific seasonality, are extremely common. And we also can make, from those before and after images, I said, some estimate of the number of block falls that are coming off. So to try and tie all this together, I'm going to try and explain it all in terms of thermoelastic stresses on these cliffs. And there's basically two types of stress that I want to talk about. One is something that is used to commonly explain like lots of cracking in ice-related features, especially ground ice, where you have thermal contraction because the ground ice cools and the ice shrinks and it eventually forms a crack. And these cracks are spaced so that the stress in the center of these polygons is basically kept to low enough values to stop the polygon from cracking further. So these polygons just like subdivide until they're small enough that the stresses in their center can't overcome the strength of the ice. Typically that needs about 1 or 2 megapascals of contractional stress or tensional stress. So if you had a curving scarp surface here, for example, and you cool all that ice, then you could form a crack that's basically orientated perpendicularly to the surface and propagating into the interior. And it won't propagate forever, right? At some point, the amount of cooling will not be enough to generate enough stress, and you'll have a certain depth that these cracks propagate to. So that's the first kind. The second kind of stress, though, is related to thermal expansion and heating. And this is a little bit harder to understand. So you have heating here, which warms up these scarp faces, and that causes compression. So in concert with surface curvature, that can produce some very interesting sorts of effect. And we have this in Yosemite Park as a good example on Earth here, where you have regional compressive stresses of a couple of megapascals. They're just tectonically driven. These aren't thermal stresses. And you have these curved surface curvature in these granitic domes, and it can generate these sheeting joints where you have a crack that's parallel to the surface or just below the surface. So it's a little hard to intuitively understand, and my PowerPoint art skills are limited, but here's an idea of what may be going on, right? So you've got a flat surface here. If it's a compressional situation where things have heated up and the ice is expanding, you can imagine each little cell in the ice here expanding, so they're all pushing against each other. And while that might cause the ice surface to inflate upward due to that expansion, there's no side-to-side movement here because each one of these little cells are basically pushing just as hard against the others as the one next to it. But if you add in surface curvature so that parallel to the surface, you're pushing parallel to the surface here, but that direction is not quite parallel to the surface and the cell beside you, then you can have some vertical stresses introduced. And if you can do that, and if those vertical stresses can exceed the weight of the material due to gravity, then you can basically pop these things off the surface and form a surface parallel sheeting joint. So the strict criterion for forming those depends on that surface curvature and on the compressive stress. So you can measure the surface curvatures in these with these principal surface curvatures, capital 1 and 2. You have some sort of compressive strength, sigma, and if you can overcome the gravity adjusted for the slope, then you can basically form a surface parallel sheeting joint. So 2 megapascals in contraction was enough to fracture the ice. So just as an example, I put in 2 megapascals and the curvatures we get from a filtered version of this high-rise DTM, and the red areas show which parts of the scarp would be susceptible to these sheeting joints, basically all over the place. So that's just one example with 2 megapascals, though, but it gives you an idea that it's not hard to form these sheeting joints in this sort of situation, given the curvatures of the scarp and the likely stresses that we have. Okay, so to get at thermoelastic stresses, then we need to get at temperatures. And so for the next couple of slides, I'll try to describe how I do that and the different sort of obstacles or shortcomings we need to overcome in order to accurately describe this. So all of these results will be in one dimension. So we're looking at just like one patch on the scarp here, and the only dimension we're looking at is into and out of the scarp, like perpendicularly to the surface here. So there's thermal conduction in and out of the scarp. We've got sunlight and atmospheric radiation coming down and hitting the scarp. There's exchange of reflected and emitted radiation with the surrounding terrain here. Since these are steep, half of the field of view of these scarps is basically taken up by the surrounding ground and not by the sky at all. And then there's thermal emission just into space as well. It's kind of interesting in that we have a vertical surface that's at the poles. So the sunlight's coming in, quasi-horizontally in the spring here. And so the times that are most important for heating the scarp, when the incidence angles on the scarp are at their lowest, and the sun is shining most directly on the scarp, are the times when it goes through the most atmosphere. So that's the first thing that needs to be well described here to estimate these temperatures, is what the atmospheric radiation is. It's an unusual situation. So to do that, I use a pseudospherical radio transfer technique using the DISORT code, which like a bunch of people here are probably familiar with, but not to belabor all the details, but do come talk to me later if you're interested. I can take the atmospheric parameters from something called the Mars Climate Database. So this is built from spacecraft observations over decades, but kind of intelligently interpolated, if you like, with a global climate model to fill in the local times and seasons that they don't have coverage in. So there's a Mars Climate Database, which gives atmospheric temperature and pressure as a function of time, and the aerosol distribution, and then there are optical properties of these aerosols that we can plug in as well. So that gives you an idea of what the radiance is coming from all directions here. But these scarps don't look at all directions, right? They're looking only in one direction. So after you mask out the directions that the scarp can't see, and you adjust those radiances for the angle that you're looking at the terrain, then the fluxes actually look something more like this. So this is the sun moving across the sky. As far as these scarps are concerned, the suns rise in the east, they pass directly overhead and set in the west, just like a patch of ground on the equator. So these scarps are behaving more like equatorial flat ground than they are like polar terrain. Around the edges of the field of view, so this is the scarp's horizon here, there's hardly any flux here because everything you're observing is so foreshortened. Okay, so the general approach is to generate lots of lookup tables, and you can see that there's lots of radiance coming from the sky here, but also a lot of energy being reflected by the bright, frosty terrain that surrounds the scarp as well. So a lot of the energy actually comes from reflection of the sunlight off the surrounding terrain. The same is done with the thermal calculations of thermal radiation. This is just from 5 to 40 microns. So again, Mars Climate Database, calculate radiances, and then mask it with the SCARPS field of view, and you end up with the thermal radiation that the SCARP sees. So this ends up being dominated completely by the thermal emission from the ground. The sky is so cold, basically, it doesn't provide much thermal radiation, except when you're looking through extremely long path lengths, like right down here near the horizon. Okay, so the second major thing that we need to understand to figure out what the temperatures are in these scarps is how much dust is covering them. Because dust on Mars is extremely thermally insulating. So you can have like a styrofoam cup, for example, that's full of boiling water, and you can hold boiling water in your hand because there's 0.5 centimeter of insulation there. But the dust on Mars has a lower thermal conductivity than styrofoam, so it can support like enormous thermal gradients and effectively squelch all the thermal variation for anything buried underneath it. Even 5 millimeters would be plenty to cover up the ice and not have it feel the thermal effects of the Martian seasons. So knowing this dust cover then becomes pretty critical to figuring out what's going on here. And just from the images where we see lots of slumping dust on the shallow troughs, but lots of jagged textures on these scarps, you can kind of intuitively think the dust cover is probably much less on these scarps, but how much less is still an important question. But there's one thing that we can use to try and figure that out, and that's when and where CO2 frost condenses. So the more CO2 frost, or sorry, the more dust you have on the surface, then the more that CO2 frost is prone to condense there because the surface is able to cool down a lot in winter. So if you look at season along here, so this is winter time, this is spring equinox here, LCBS 360, and then early spring. For different levels of dust cover, you can have very different amounts of frost that condense here. So one of the things we can do with HiRISE is an experiment where we take very early images, like in this 340 to 350 range, and try to figure out if the scarps are dust covered or not. And we've been able to get a couple of these images. So LCBS 342 and 350. I mean, this incidence angle here is above 90, so the sun isn't even above the horizon yet. It's still twilight. Here, the incidence angle is, 88, so the sun is like right on the horizon. But you see in all cases that these scarps are still dust-free, are still frost-free, excuse me. So that indicates to us that the dust is probably a millimeter or less, and so not playing an important thermal role, which makes my life a lot easier. So I'm very happy to get these images. Those two images here, these are these LCBS marks where the red lines are. With zero dust here, you can still get a small blip of CO2 frost here, but it's only a couple of tens of microns or something like that. So maybe that's there, maybe not. We haven't got HiRISE images filling in this area, but in either case, it's not playing a significant role anymore. The dust is not playing a significant role anymore thermally. Okay, so with all of those caveats and models joined together with shoelaces and duct tape, we have a way to get temperatures on this scarp front. So there's several plots that look like this. So let me just stop for a minute and explain what we're looking at here. This is a 1D model. So time is in the x-axis here, and that dimension of depth from the 1D is on the y-axis here. So the surface is up top or close to the surface. And then you get deeper and deeper as you go down. It's a nonlinear scale, not exactly a log scale, but nonlinear nonetheless. So all this is very near the surface, just centimeters. Then you get down to the tens of centimeters and then sort of meters range. This is linear in time, which is a little bit nonlinear in LCBS. So you probably notice that 60 to 90 is much further apart than, say, 240 to 270. But it's linear in time, and the color is temperature here. So you can see when the sun comes up in the spring at LCBS 0, this big pulse of heat gets conducted into the interior. And then as the sun sets again for the season at LCBS 180, that cools off, excuse me, and then the temperature drops at the surface until you get down almost to the frost point. This is almost getting down to the 148 or so that you would need to condense frost here. So we can take these temperatures, we can plug them into a a model that converts temperatures into thermal expansion or contraction, and so into stresses that are compressive or extensional. So this model actually comes from Mike Mellon in the 1990s. It's for a homogeneous viscoelastic solid, so it's kind of semi-infinite in depth, and it's unfractured. And I'll mention what the fractures do to the answers in a moment. But it's been used successfully to calculate, or to simulate the formation of these Martian polygons, for example, before. Okay, so you have stresses then that build up because of temperature changes. You can imagine the ice in its rest state here. There's 2 points on the surface, A and B, that are a certain distance apart. When you cool it off, everything shrinks, but A and B stay the same distance apart, because although they might want to like pull themselves together because the ice is shrinking, they can't, because there's ice off to the left and off to the right here that are pulling them in the opposite direction. So they're basically kind of just stuck there. If that shrinkage gets high enough and the stresses build up enough, then a fracture will form, as we described earlier. But for now, these two A and B points are kind of stuck at the same distance apart. The same is true when the ice heats up and it expands. So perpendicular to the free surface, it's free to expand as much as it wants. So there's no stresses in the vertical direction here, but considerable stresses can build up in the horizontal direction as the ice tries to expand sideways, but it can't, because the ice to the left and to the right is also trying to expand sideways. So one way of saying that is that horizontal strains are zero and horizontal stresses are created, and vertical strains are non-zero and vertical stresses at the surface are zero. So we're going to switch those horizontal and vertical notations to just being parallel and perpendicular to the scarp front when we go forward talking about that. So these scarps, they're breathing in and out thermally by a couple of centimeters each year, and stresses are coming and going a lot as well. I promise this is the only set of equations I'll show, and it's already in cartoon form. But I just wanted to say that the way we put this together is we have thermal strains rather, that have an elastic and a viscous component, and then we can just differentiate all this with time. So the rate of change of these thermal stresses is the rate of change of the elastic stresses and the rate of change of the viscous stresses. And this rate of change of viscous stress, that is due to the ice deformation that happens in the same way that glaciers flow downhill or ice caps spread out. And viscous deformation has a bunch of different physical causes. So they're basically added up in a way that looks something like this. But the important part is that some of them are grain size dependent. So we needed to know the atmospheric behavior, the dust cover, and this is like the last component that we really need to understand in order to be able to simulate the stresses here. And so next slide, I'll talk a little bit about that. But when you fill in all of this, then what it basically yields is a differential equation where the rate of change of stress is dependent on the stress, the temperature, how fast the temperature is changing, and this ice grain size. So once we sort this out, we'll be able to figure out what the stresses actually are. Okay, so ice grain size is something that we can't measure on Mars because nobody's there digging into the ice cap for us, unfortunately. And because of the dust cover on most of the troughs, we don't really get a spectral determination of what the ice grain size is either. So one thing we can do is look at the ice grain behavior on Earth and try to think about what is probably going on Mars. So on Earth, ice grains grow steadily with time because larger ice grains can scavenge water molecules from smaller ice grains. And all of these ice grains are constantly shedding and reacquiring water molecules while they're in this polycrystalline collection here. Because of the different surface curvatures for large and small grains, large grains grow and small grains tend to not be as successful growing. And so large grains eventually end up growing and small grains shrinking, and then the ice grain size keeps going up. But it can only go up so far because these grain walls can't expand past little dust grain impurities that are inside the ice. So this produces a kind of maximum grain size that you can have in terrestrial glaciers. Now, on Earth, that doesn't matter all that much because this effect is limited for two reasons. One is terrestrial ice is really clean compared to Martian ice. Like Earth glaciers are very, very clean. Martian glaciers are very dirty by comparison, or dust-filled. The other reason is that terrestrial ice flows a lot, and the shearing of the ice basically breaks up these grains and resets the grain size down to smaller levels. So we don't have a lot of ice flow on Mars. It looks like this North Polar layer deposits does not float at all based on its internal stratigraphy. And we do have a lot of dust. So both of those indicate that this is probably the limiting mechanism for grain size here. How much dust is a good question. And we can have radar data that basically penetrates all the way to the bottom of these ice caps. And based on the timing of the radar pulse and the losses of the energy, it seems that the ice has only a few percent of dust in it at most. So maybe less than 5%, probably less than 3%, but it's down in that range. It's probably not like down as far as 1% because then you wouldn't be able to generate the sublimation lags needed to protect those troughs. So 1 to 5% is probably a good range to go for. With this Zener pinning mechanism, these are the sizes that the ice grains can grow to for different dust fractions on Mars. And there's different ways you can distribute the dust grains. But let's just look at this uniform case here because that's probably the easiest. So this is the dot dash line here, and it kind of shows you what the grain size would be for different dust contents. So it can be anywhere from like 10 microns for the very dusty case of 5% down to closer to like 100 microns for the dust-free case, or almost dust-free case. So 10 to 100 microns for the ice grain size is probably a good thing to go with for now, based on what we know of these Martian ice caps. Okay, so now, after all that, we were able to actually calculate the stresses in this one-dimensional model of these scarp fronts. And as before, we've got time along the x-axis, depth on the y-axis, and these two panels are for the two ice grain sizes of 100 microns and 10 microns. So you can see, first of all, that the 10 micron stuff squelches a lot of the stresses. So the contractional stresses get up to 10 megapascals in the winter when ice grains are large, but the smaller grains, which flow more efficiently, are able to dissipate a lot of those stresses. So it tops out at about 6. Not that that matters much because 2 megapascals is enough to fracture ice anyway. So in any case, we're looking at being able to form contractional fractures, so perpendicular to the surface, pretty easily in the winter. The other interesting feature of the stress behavior is this thermal wave that passes into the ice here that heats it up at deeper and deeper depths as you go into the spring and summer. So this causes expansion of the ice and the compressive stresses that we were talking about. And that also is squelched by the smaller ice grain sizes, but still present there over this time period. We can simplify this a little bit to just show in cartoon form what's going on here. And so what I did, I just color coded this so that significant tension, so greater than 2 megapascals, is in the brown. Significant compression, so less than minus 2 megapascals, is in the blue here. So there's a lot, and everything else is just green. It's kind of like meh stresses. There's a lot going on in the upper few centimeters, of course. These little pinstripes here are all the diurnal variations of heating and cooling. So sure, in the top couple of centimeters, there's lots of action. But in the meter-sized chunks of ice that we see flaking off these cliffs, we're looking for bigger things than that. So like here we've got the blue areas here for this compressional wave, and the brown areas that propagate deeply then for the extensional wave, or the extension. Okay, so the suggestion is then that we can form two types of fractures here. We can form these sheeting joints in this time of year when we have this compression going into the surface. So this produces the surface parallel fractures that look a lot like Yosemite. And then in the winter, we have the thermal contraction that produces these fractures that are perpendicular to the surface. So looking a lot like polygons that you'd form in some sort of Arctic environment. So these scarps can be chopped up in two ways. You can chop them up perpendicularly to their surfaces, And so you can generate these like slabs of a certain size. And then you can cut the slab off from underneath, parallel to the surface, so that they're able to basically drop out of the cliff face and fall down. So how does that compare to the timing of the avalanches? Well, it's pretty interesting, isn't it? It's the avalanches are all here in the LSS, say 5 to 50 range, or 10 to 50 range, and the compressional stresses match up with that almost exactly, at least for this ice grain size anyway. And the time when these when these avalanches are most common in the 35 to 40 range, that's more or less when the compressional stresses are covering a depth range of like a couple of meters or so, which is similar to the size of the blocks we see falling out of these scarp faces. So it's definitely very suggestive that these compressional forces that are able to chop up Yosemite's domes into surface parallel sheets like this can do the same and produce this kind of slab-like texture on the Martian scarps and cause a lot of the block falls that we see. Okay, so I did promise more of a Yosemite analogy here for the avalanches as well. So here's one of the Yosemite rock falls caused by those surface parallel sheeting joints. And you can see what happens when this stuff hits the ground. There's like this billowing scarp front that is propagating down this lower slope here. So that's pretty similar to what goes on these Martian avalanches. We've got like a fast drop down this ice cliff, which is hundreds of meters high. Remember, so by the time these ice blocks have reached the bottom, they've probably pretty much pulverized themselves by bashing against the scarp front. And this stuff races out in this billowing cloud front by a couple of meters per second, as we can see in those high-rise images. So I would say that the correspondence then between the seasonal timing and the type of stress needed to form these sheeting joints, the size we expect these blocks to be, and the depth of that sheeting joint, those sheeting joints, and the fact that these falling blocks in other situations are very good at pulverizing themselves into dust-sized particles and rolling out like this, all sort of points towards a very similar situation between the North Pole of Mars and Yosemite Valley on the Earth. Okay, so just to try and wrap up then, trying to summarize a little bit of where we are, and then we have some time for questions. We have wintertime tensile stresses that can propagate vertically into these cliff faces. They chop up the cliff face into these sections a couple of meters across, much like thermal contraction crack polygons. We've got springtime compression from the heating that propagates into the subsurface and generates fractures parallel to the surface that are probably a couple of meters down. These can explain the block falls and the scarp appearance in that qualitative ways, but also matches the seasonality of the avalanches in a very quantitative way as well. The heating is sensitive to atmospheric aerosols, so that is potentially a mechanism to explain the interannual variability. So we saw this long-term trend of decreasing avalanches with year. And so this is sort of where I'm at the point where I'm actively investigating this part now, is about whether we can take the small variations in atmospheric aerosols that we see from year to year on Mars and explain the differences in the number of avalanches we see there as well. Because the sun is coming in almost horizontal and through this enormous path length of atmosphere, tiny fluctuations in the optical depth of the aerosol column can actually have like big effects on the heating rate of the scarps. In any case, I think we've got this neat runaway effect where we've got these scarps that are basically, because they're so steep, they're able to generate these large thermal stresses, which generates block falls and avalanches. Those block falls and avalanches scour off the dust really effectively. And the lack of dust basically allows this process to continue because you don't have a lot of thermal insulation accumulating on the surface. So in some ways, this is like a self-perpetuating engine at the moment. And it's a little bit hard for me to figure out how one of these shallow troughs, which are dust covered and very immune to thermal stresses because of that, can evolve into these very steep cliffs. But right underneath these steep cliffs, there's a sandy, unconsolidated layer called the the basal unit, and an erosion of that may be enough to undercut this steep scarp front and initiate this cycle. And once you get into this cycle of avalanches constantly scouring off dust, and then thermal stresses being large enough to cause new fractures, then it's self-sustaining and these cliffs can just keep retreating after that. Okay, so that's about all I had today. So I'd be happy to take any questions, and thanks for coming, for your attention.
Shane? Jenny?
Yes.
Can people hear you, or do you have?
I can talk really loud.
Okay.
Very nice talk, Shane. I really enjoyed it. Two questions for you that I think are related and hopefully should be quick. One is, have you been able to estimate the rate of cliff erosion from these avalanche processes? And secondly, have you been able to use a really nice high-rise DTM that Sarah made and company made to estimate the volumes of erosion off the cliff versus the volumes of erosion sediment that accumulate on the floor? Is that?
So the second part is easier to answer than the first. There's not enough material to measure differences in a DTM yet. We would have to stick around. High-rise would have to function for about another 50 years. Alfred, is that on the cards?
Yeah.
Yeah. So decades maybe before we could answer that with a high-rise style DTM. But we can see how many locations where things have changed and get an idea of the average block size, and so the average retreat rate of this. And I think it's close to about 1 millimeter per year. So it's not enormous, but if this polar cap is a couple of million years old, then that could be significant.
So if I can follow up on that, does that mean that the polar cap is shrinking, or is it flowing to make up for that loss?
Probably shrinking. So the indications from the internal stratigraphy are that there's nothing moving there at all, flow-wise.
Nothing that we can resolve, but this would be a very slow motion.
Yeah. I think it's probably shrinking because these cliff faces that are steep, they continually form in these arcuate sections, and so you can see it's being eaten back into the polar cap. So it's there's no enhancement of the flow there that's making up. It's not fast enough to make up.
Lynn.
Are the blocks lithic or ice or a combination?
Almost all ice, but with a couple of % of dust in it.
Okay. But there's not big rocks there.
No, they're boulders, but they're ice boulders.
Ice boulders.
Yeah.
And we do see those blocks shrink over time too. So
yeah,
they're going away.
Do you also see those avalanches in the SPLD or mid-latitudes, like in the ice exposures?
Mm-hmm. No, it's a good question, but we don't. And I think the reason for that is the SPLD is mostly got dust all over it. Even on the scarp faces, it never gets steep enough to slough off that dust cover. So I think it's so thermally insulated that it can't generate the thermal stresses needed. The mid-latitude ice scarps, so that's an interesting one. But in that case, they're all pole facing. So they spend almost the entire year in shadow. And they probably don't get the extreme springtime heating that these scarps get. These scarps, because they're south facing and they're right at the pole, so as soon as the sun clears the horizon, they're getting like full on normal insolation.
Follow-up question on the NPLD. There is this linguid shape. Does it provide an isolation, or you also see avalanches within the linguid?
Oh, you mean like Chasma Boreal? Yeah. So there are some avalanches at the head of Chasma Boreal where there are some steep scarps that look something like this, but most of them are up around that area at a 180 east longitude. So at the top of the polar map.
Are there questions online? Just speak up. I don't see any questions in chat. I'm not sure if there's someplace else I should look for them.
Ty?
Question not well formulated yet. It's getting towards the variability on longer than annual timescales, which is super interesting. I guess I didn't get a sense of are these avalanches occurring preferentially in certain places, or are they distributed fully around the feature such that if they're fully around, you need kind of global scale variability on these time scales, but if they're more located, then you need kind of regional scale variability. Can you speak to that?
Yeah, so a lot of them, I'm gonna go all the way back to this. I think the map at the beginning might be the best summary of where these things are. Yeah, so this map here shows all the scarps that are above 35 degrees, but they don't all have avalanches on them. So almost all the avalanches are in this sector here. So it's about 90 degrees of longitude or so. Like there are a couple, like what Roberto was asking, where they're at the head of Casmo Boreal, but they're almost all of this area. So, you know, it's several hundred kilometers, like close to 1,000 kilometers probably, for that zone where these cliffs can form. But it's not global.
Do the directions of the avalanches tell you anything about like aeolian activity at the sites?
So they run downhill, and we haven't seen any evidence of like the cloud being blown in one direction, like the cloud being sheared off in any direction. So as far as we can tell, the atmosphere is relatively still on these things from that end. But they don't last very long, so maybe there's not enough time for the wind to shear them, but at least it indicates that they're not like super strong winds, like going parallel to the scarp front.
Is there enough data over time to be able to assess if a particular region or location is active 1 year? Is it more or less likely to be active with these falls the next year?
Yes, but that analysis hasn't been done yet. It's a good idea, though.
Aren't there strong katabatic winds coming off the polar? Or is that next to the season?
It is in a similar season, and they would come off more or less perpendicularly to the scarp front here. So it would help the avalanche cloud move outward. But you know, these winds or this airflow should detach from the surface as it passes over the scarp front. Anything, you know, higher than 30 degrees or so should allow for that. And these things are so steep, I think there must be in a wind shadow.
What triggers these avalanches, or is it so tiny that it could be anything?
I think it's these surface parallel cracks that are just like propagating further and further. Is, you know, every time you go through one of these heating cycles, the crack propagates more, and eventually it will just connect up to the surface perpendicular scarp fractures, and then the block will just tip out.
Let's call. Okay, thank you, Shane.
All right, thanks everyone.